All right, this is part 2 of my thorough differential topology series. And just like a dating coach, I'm here to explain to you what it means to be smooth. In pursuit of that goal today, I'm going to go over what it means to be a smooth submanifold using a slightly older sort of definition for the object, but one which much more mirrors the sub-object relation found in other categories like the category of groups that we study in abstract algebra, or the category of subspaces that we found earlier in general point set topology. So with that explanation out of the way, I'll get on to our first definition. All right, so here we are. What it means to be a smooth submanifold. First of all, we're going to require that we have a smooth manifold n to talk about, and a smooth manifold n is going to be called a smooth submanifold of another smooth manifold m if, first and foremost, n is a topological submanifold of m, which, if we don't recall what that means, it means that n, which we already know is a manifold, is a subset of m, which we already know is a manifold, and moreover that the subspace topology that n would inherit from intersecting all of m's open sets with it would also coincide with n's natural topology as manifold. If that's the case, then we know that n is a topological submanifold of m. And then we say that not only is it a topological submanifold, but it is in fact a smooth submanifold if the smooth structure of m and the smooth structure of n agree in the following way. Namely, their union contains only any meaningful transition chart, that is, transition charts made from overlapping domains in that set, must be smooth. If that's the case, and this, by the way, is very similar to our old notion of atlas compatibility, I'm just not requiring that this be necessarily an atlas of anything. I just require that these transitions be smooth now. And if they are, then we will say that these objects have the smooth submanifold relation between one another, namely that n is the smooth submanifold of m. And this very closely mirrors the sub-object relation that we find in other categories, because all I'm really asking is that n is a subset of m, and then their topology agrees and their smoothness agrees. And that's really the only structure that we've added to sets here in in differential topology. We've only added smoothness. So this we all got, the topological submanifold part we got from normal point set topology, and now we're adding on our new bit of the definition so that it respects the smooth structure that we've added here in differential topology. All right, so now that we have this definition, I am going to prove some propositions and then talk about some examples. So let's get to that. All right, so now that we have a working definition of smooth submanifold, I'd like to produce a smooth submanifold test that's a little easier to work with than satisfying my definition. My definition called for checking all of the chart transitions inside of the union of two smooth structures. And smooth structures are big sets. We might not even always want to write them down, as I said in the first part. And so what I'd like to show you now is that it's sufficient to just check that the union of two atlases on our tooth manifolds ends up containing only smooth chart transitions in order to show that one is a smooth submanifold of the other. So let me begin that proof now. All right, so because we know that atlases generate smooth structures, let AN be any smooth atlas that generates n smooth structure Sn, and likewise let AM be any smooth atlas that generates M's smooth structure Sm. So what I'd like to show is that any choice of chart transition in my union of these two sets, Sn and Sm, must be smooth just by assuming these guys have a compatible union. So let's assume, as stipulated up here in the claim that I'm making, let's assume that the union of these two atlases, AN and AM, has only smooth chart transitions to work with. All right, so when I get to the next slide, I'll show us how that helps. All right, so let's let these two charts be any two charts in my smooth structures, Sm and Sn, such that their open set is not disjoint. It's got a non-empty intersection. Then for any single point P inside of this intersection, because P is then got to be inside of both N and M, both of our manifolds, and our atlases, AM and AN, cover M and N, it must be that there is some chart in AM and some chart in AN such that P is in their intersection. And this is because there is some chart in AM that contains P, because P is in M, and there's some chart in AN that contains P because it's in N. And then their intersection would therefore also have to contain P. So it would be non-empty. And then by our hypothesis, these two smooth atlases, they need to have only smooth chart transitions. So the chart transitions that we form with these two functions here, these two charts, are going to be smooth maps. So now we can use these as a way to build smooth restrictions of the transition maps between these guys that will allow us to conclude that they're smooth. All right. Now, to make it a little bit easier to write down, I'm going to rename this gigantic intersection, which we know is not the empty set because P has to be in it. I'm going to rename it W, and we'll know that it's in fact a subset of N because these sets, UN and VN, are both subsets of N, and N is a subset of M, so everything has to be a subset of N in the end. All right. So, and it's also an open set because it is the finite intersection of a collection of open sets. Moreover, the restrictions that we get by restricting down to these open sets, the homeomorphic images of these open sets, must be smooth because the restriction of Euclidean smooth maps to open sets in their domain must be smooth. So we know these are smooth. And similarly, because AM, our atlas on M, generates our smooth structure, SM, it must be that our two charts, XM and YM, have smooth transitions on their domains, which are the images of UM intersect VM with under XM and YM. However, when we can then restrict them in the similar fashion that we did up here to the open set W and get more smooth maps. So far we're getting a collection of smooth maps. And so what we did here with SM and SN, you could just replace N for M and get the argument for the other functions. So all 6 of these transition functions are smooth. The ones between XM and YM, the 2 ones, the ones between YM and YN, the 2, and then the one that I haven't written down here, but you could get just by switching switching M and N down here in the bottom case, and that would give you YN and XN. So knowing that all of these are smooth when they're restricted down to this open set gives us the very, very last slide here, which is where it all comes together and we find out that our transition is smooth. So let me write that down. Okay, so if you believe me that all of those other transition maps that I gave you are smooth, then what we finally get is combining all of them together, this particular one here, will give us a restriction of the transition maps between XM and XN, which will be smooth because it's a composition of smooth maps up here. And it won't be the entire transition map between XM or XN, but it will be smooth, a smooth restriction to this open set W. And since P was selected arbitrarily inside of the intersection of the open sets UN and UM, and we can always find such a W that has a smooth restriction, it must be that the actual whole functions themselves are indeed smooth. So that concludes the proof, and it must be that all the chart transitions between SN and SM are in fact smooth, just by assuming that the atlases are smooth. So this is a much more manageable test. You can actually do it for one thing. You don't have to go out and get a smooth structure. You can just test your atlases. And so if your atlas is nice and easy to work with, this test can be quite manageable. So it's the test that I will be using to show things are submanifolds if I venture to do so. So next will be some different manifolds and submanifolds. All right, I've got a selection of propositions here, which are actually fairly simple and straightforward to prove, so I'm not going to spend too much time on them. I just wanted to let you all know that these are examples of some of the other smooth manifolds that we can build with smooth manifolds that we know about. So for one thing, an open subset of a smooth manifold is another smooth manifold. This is not too hard to see why. It's clearly a topological submanifold in the same definition that we get from topology, but it's a smooth submanifold when we equip it with the restriction structure from the original smooth manifold that it came from. So I take the smooth structure on that manifold and restrict all of its charts to their intersections with my open set, and it gives me a smooth structure on my open set, and they have to be compatible because it in fact has to belong to my original smooth structure. So that's all that really needs to be said about that. Two smooth manifolds, M and N, can produce a third smooth manifold, their Cartesian product, M times N, when equipped with the Cartesian product structure. So that is, for any two charts, any chart in M structure and N structure, you can form the multiplication chart, the product chart, by simply making the pair of both of them, and it will cover both M and N, or the product of M and N, because SM covers M and SN covers N. So that's all that needs to be said about that. That's not too interesting. And the last one is where I have a little bit more writing, and that is that if I have two smooth manifolds that are of the same dimension, so that's what that tiny writing up there in between the margins is, if they are of the same dimension and their intersection is empty so that they are disjoint, then it must be that their union is a smooth manifold where the smooth structure that I'd be placing on them is in fact the union of the two smooth structures. And it's clear that we're not going to have any sort of weird pathology from intersecting two manifolds show up because there is no intersection. And likewise, the manifolds are both certainly covered and smooth because their original manifolds that they made from were both covered and smooth by their smooth structures, excuse me. So then the last thing that I have to explain, even if they aren't disjoint, these two smooth manifolds M and N, we can still form a union smooth manifold from them, but it will be using the disjoint union. So if you don't remember what the disjoint union is, run back to Wikipedia or set theory. It's like a union, except that I am unioning up ordered pairs that contain elements in the things that I'm unioning, and an index variable so that they're always separate from one another. This way, it's the reason why it's called a disjoint union is because it makes things that aren't necessarily disjoint into disjoint sets to union them up. All right, so these are some propositions. They're not too hard to prove. That's why I only gave a few words on them. But they'll probably come up here and there as we do our work. So we'll have to keep them in our minds. All right, so now with those more minor propositions out of the way, I'd like to start getting to some examples of smooth manifolds and their submanifolds. So I'd like to do one. I'm going to cover Rm and some of its submanifolds, and then I'm going to talk to you about the spheres. But for right now, let's just focus on Euclidean space. So we've spent all this time coming up with our definition of smooth manifold and smooth submanifold in hopes of making spaces that approximate Rm. We should hope that Rm would be one of these spaces, and in fact it is, because it's clear to see that Rm is a topological submanifold, or topological manifold rather, not a submanifold. But to see that it's smooth, we can actually just check out one of these atlases that contain a single chart on Rm, and that chart being the chart that covers all of Rm with the identity homeomorphism. And that thing is trivially smooth because it has no chart transitions. So this generates a smooth structure, and that smooth structure together with Rm form a smooth manifold. So now let's look into seeing why the subspaces of Rm are smooth submanifolds of this, what we already know is a smooth manifold. And that'll be on the next slide. All right, so now on to that linear subspace of Rm. So let L here be some linear subspace of Rm, and if it's a subspace of Rm, Rm is finite dimensional, so the dimension of L has to be less than or equal to that, so it has to also be finite, some number n. And that also means, because it has that finite dimension, that there exists a set of basis vectors v1 through n, such that any vector v in our subspace L can be represented as v being equal to the sum of ci vi from I equals 1 up to n, where I'm using the Einstein summation convention, where anytime I have that index repeating twice, I'm summing it from 1 up to my dimension in that space. So so every single vector in L has a unique representation as ci vi in one of these ways. Then I can define a linear transformation T from my linear subspace to Rn by T takes in V, which we know has this representation, and sends it to the vector, the coordinate vector, Ci going from I is equal to 1 to n for all the different coordinates. So C1, C2, all the way on to Cn. So, and then it has a natural inverse then that takes in that vector that I gave you, C1, C2, down to Cn, and sends it back to its vector representation in L, where those Ci are just the coefficients of the Vi. This then is clearly, so we've clearly got an invertible function here, and it's also not too hard to see that it's linear. So this is in fact a vector space isomorphism between L and Rn. So, but we don't really need that it's a vector space isomorphism. All I need is that it's a homeomorphism. But the reason why I wanted to say that it was a vector space isomorphism is because it's in fact a vector space isomorphism between finite dimensional vector spaces. So because that's true, and some other stuff from functional analysis, it's the case that both T and its inverse, T inverse, both have to be continuous. So I have a function which is continuous with a continuous inverse from our subspace L to our subspace, to Rn, and just this T and L itself, that makes up an atlas now on L. So now all that I have to show you, and it's an atlas particularly with one chart in it, so just like the one that I showed you for R, it's trivially smooth. Now to show you that this subspace with this atlas is in fact still a smooth submanifold of Rm, I just have to show you that the only two chart transitions that I can form using these two atlases are, they happen to be smooth as well. So I will write that down and show that next. But so far we know that we've got L, we've got now a possibility for a atlas on L, which is just the chart that goes from all of L using the transformation T that I've defined here, which we know is a homeomorphism from all this work that I've got. So now on the next slide we'll be showing that not only is L a smooth manifold, which is what this demonstrates, but it is a smooth submanifold of Rm. All right, so we know that Rm is an M manifold. We know that L, its subspace, is an N manifold. Now I just have to show you that it's in fact a smooth submanifold of Rm. So to do that, let's remember that we've now talked about these two, what we know are smooth charts, but they're trivially smooth because they only have one thing in them. And that's the chart on Rm, which is just the one that has Rm in its identity map, and then the chart on L, which takes L and uses the transformation T that we defined earlier. So that means we really only have two different transition maps to consider, where we've made the transition map with these functions in opposite order. So that's what I've got written down up here. And we can see, because what we're actually doing is composing the identity map with something here, a restriction of the identity map, it's actually just going to give us back the original object here on that restriction. But since that restriction is the domain of our original object, it gives us back the whole thing. So we only really have to worry about the smoothness of these linear transformations T and T inverse. We know that they are linear transformations, and we know that they are acting on finite dimensional real vector spaces. So, you know, we really only have we don't have any more work to do here, because it's kind of just a fact from linear algebra and vector calculus that such a transformation, a linear transformation on a finite dimensional real vector space, is in fact smooth. It's just, you know, if you wanted to convince yourself, go back to the definition of what it means to take the differential of an object, of a function, in a Euclidean space, and then try doing it with a linear transformation, and you'll see that it's very, very easy and it always works out. So that's this shown. It is in fact true. These two charts must be compatible because these two functions must be smooth. So it must be that any subspace L that we could choose of Rm is in fact a smooth submanifold of Rm. So so this is the primary example of a manifold. You know, there are obviously other manifolds that people are interested in, like the next one I'm going to be talking about. The last example for this video is going to be the sphere. But this was the primary motivating example. It was the discussions of Euclidean spaces that got people to thinking about how the techniques that we use here, taking limits and finding linear approximations to things, can extend to other more general abstract surfaces that we might need these tools in order to understand. So like, for example, if I wanted to calculate lengths of curves on something crazy and abstract that I didn't necessarily know fit inside a Euclidean space. All right, so now for proposition 6, the last example here for this video, before I move on to our next topic, which is going to be defining smooth maps. And this is just going to be the one of the prototypical, really common examples of a smooth manifold. When people think about shapes, it's one of the first things that pops into your head. And it's the sphere. And here I'm going to give a proof that the n sphere, Sn, of any dimension is in fact a smooth manifold, according to the definitions we've been working on. And you could probably imagine a whole lot of smooth submanifolds of it, but I simply don't have the time to get to it right now. I will be including some of those in future videos. So for the moment, let's just recall from general topology, from the topology of manifolds, that Sn is in fact a topological manifold. Specifically, I want to refer to the stereographic atlas that you place on it by removing the north and south pole, the point that has the points that have 1 and -1 in their very final coordinate, and 0 in all other coordinates, and map the remainder of the sphere minus that point onto the hyperplane of fitting dimension. So if you're not familiar with this concept, go look up stereographic projection. I've got the maps that it defines right here. They're vectors going from the first coordinate where j is equal to 1 to the last coordinate where j is equal to n, and they'll look like this. So they'll have the xj coordinate over 1 minus the xn plus 1th coordinate. All right. So, and then the denominator having the negative sign removed here on z. And then the inverses of these are also known. I'll be using them, I'll be writing them down on the next panel here that I draw up. But all we need to show, since we know that we have an atlas here, and it contains two things, we need to show that all the chart transitions that we can make here are smooth. And there are two of them. There's the one where I compose y with z inverse, and the one where I compose z with y inverse. So let's write down the inverses to these guys on the next panel, and then we'll compose them and see if they look like they're smooth. All right, so now with all of our functions and their inverses written out here, functions up here, so I have z and its inverse, f and its inverse. And I have expressed these guys not in the collapse notation just because it's easier to kind of see what I mean here. You're going to keep using this format for the coordinates until you run out because you're only going to have n of these. And when you get to the n plus 1th coordinate, because this is mapping into n plus 1 space, you'll simply use this quantity as the last coordinate. So that's what these inverse functions are. And it turns out, so restricting their domains to their intersections, we end up getting the sphere minus both of those points, which I'm going to call v. And then when I compose the inverse of z restricted to v with y, and likewise the same thing if I do the other combination, I end up getting the exact same thing here. This map, which takes in, at every coordinate, takes in the coordinate psi and divides it by the length of whatever the psi vector was. All right, so this set of operations that I'm using to define each coordinate is smooth so long as psi never takes on the length 0, in which case the denominator blows up and we definitely don't have smoothness. But if we notice that we removed both points, both of the -1 and +1, the north and south pole, from our sphere, and because each of our stereographic projections, the alternative one, where the opposing point was actually inside the domain, always mapped that opposing point to the origin, we'll get that both of these spaces that are being mapped between are in fact just Rn minus the origin. So since the origin's gone, we don't have any vectors that have length 0 to mess this up. So these two functions must in fact be smooth on their entire domains. And since those are the only two chart transitions that we could form with the stereographic atlas that we made here on our SN, our topological manifold SN, it must be that this atlas is smooth and can generate a smooth structure which makes SN a smooth manifold. So it is true that the sphere is a smooth manifold. And this is a general construction for an atlas and then a structure, just by generation, that turns any sphere of any dimension into a smooth manifold. Now, what's special about the sphere in certain dimensions is that this isn't the only structure that we can place on the sphere. In, I believe is dimension 7, the 7 sphere, John Milner showed the existence of a sphere which has a smooth structure, which is not compatible with the smooth structure we generated here using the stereographic atlas. So that will be a discussion for later developments. But for now, we have a working definition of smooth manifold that we've used to test on some different examples. We also have a working definition of smooth submanifold, which differs a little bit from what you'll find in modern texts, but only very slightly. And I'll show, once we've defined smooth maps, that the modern definition is equivalent to the one that I've given. I've just got some theorems to prove first, but that's all part of the theory. Alrighty, so I hope you're excited to take a look at smooth maps next time. We'll see the equivalence relation that we can define on these smooth manifolds to tell when they're the same, just like we did in topology with homeomorphisms. And we'll get to see a whole lot of cool theorems about smooth functions that we kind of saw glimpses of when we studied calculus or anything similar to that. So I hope you'll stick around with me for that. I can't wait to see you.